here we have an atom, which is protons and neutrons in the nucleus. Then around the outside we have electrons. Then we have the strong interaction, which is interaction between two hadrons. And then the weak interaction is interaction between two leptons. And then we have the Feynman diagrams, which is number one, which is the electromagnetic force between two protons, where the protons collide and then they go up with a time increasing always, so it never goes in reverse. And then a neutron-neutrino interaction, so number two, with a proton-antineutrino interaction. Number three, we've got beta minus and beta plus, with electron capture at the end.
Then we have the particles, which are split into two groups. We have the leptons and the hadrons. The hadrons are then split into two groups further. The baryons, which consist of three quarks, they contain the proton, the neutron, and the sigma particles. We then have the mesons, which are quark-antiquark pair. We have pions and kaons. Then on the leptons, we have the electron and the muon, with the electron neutrino and the muon neutrino. The quarks are the up, down, and the strange, which are plus 2/3, minus 1/3, and minus 1/3. Then the antiquarks, which are minus 2/3, plus 1/3, and plus 1/3. We then have the exchange particles. So for weak interaction, we have the W plus, W minus, and Z0. And then for strong interaction, we have the gluon, and for electromagnetic interaction, we have...
Today I'll be demonstrating the gold leaf electroscope, which shows us why light is definitely not a wave. If you look closely, this negatively charged zinc plate loses its charge as this ultraviolet light, which isn't on yet, hits it. As you can see, the gold leaf is slowly returning to its original position, which you didn't see because we charged it beforehand. This is because the frequency of the light is higher than the threshold frequency of the metal, which is the work function divided by Planck's constant, and then... that'll do. If it were equal to this, if HF equaled the work function, the electrons would be liberated, but with no kinetic energy, as the maximum kinetic energy is equal to the energy of the photon minus the work function of the metal, which in this case is zinc, and there's a different work function for every metal. If we were to increase the intensity of this light, which we can't, you would see that more electrons are released as the gold leaf would go down faster, but with the same energy, as intensity does not increase energy, because light is definitely not a wave.
Hi there. Today I'm going to be talking to you about ionisation and excitation. Here we have two electrons and a nucleus. One electron is just orbiting its nucleus, and another electron hits it, but with not enough energy to actually liberate the electron. This causes excitation to a higher energy level. As the electron de-excitates back down to its original energy level, it produces photons of different frequencies depending on the jump it made. That's right. Hello again. Now I'm going to be showing you what would happen if a photon hit an electron and didn't have exactly the same energy. Here again, we have the electron orbiting its shell, or its nucleus, when a photon of too small energy will hit it and not affect it at all. This occurs because a photon cannot be split in two.
So does the photon stop?
Energy. So the photon doesn't stop, it bounces off, but yeah.
As shown by the photoelectric effect, light can exist as photons but it can also exist as waves because it is able to diffract through gaps. A guy named De Broglie came up with an equation to demonstrate this wave-particle duality, where wavelength is equal to Planck's constant divided by the momentum of the particle. One experiment demonstrated that particles can exist as waves by firing a beam of electrons at thin metal foil. These electrons were then diffracted as they also behaved as waves, shown on the screen as they turned into rings.
Okay, so we're looking at electricity and simple definitions and circuit rules. Voltage is the charge carried by each electron, and that is E over Q in its Coulomb form. And the current is the rate of flow of charge, Q over T. And if looking at circuit rules, in series, voltage is split, current is constant, and resistance adds up, and we have that demonstrated on our circuit.
Okay, in this circuit is in series, as you can see, by the wires going in series. And when I turn it on, the bulbs are quite dim because voltage is used up here, and so less voltage goes into this bulb, so it has less brightness. And then, when you change this into a parallel circuit, very quickly, then the bulbs, as you will see, will both be brighter. Glad that worked. As the voltage is the charge in an electron, and the electrons split. The voltage doesn't split, the electrons split around the circuit, but the current splits because the current is the rate of flow of charge.
Yeah, that rule goes to in parallel, voltage will be equal at all of the separate junctions, but current will be split between the junctions proportionally to the resistance that they have. So if you now go into Ohm's law.
Nice. Ohm's law states that the PD, potential difference, across a metallic conductor is proportional to the current through it, provided the physical conditions do not change. The result of Ohm's law is the equation everyone knows as R equals V over I. We have a long list of equations here, which will be provided in your exam, but learn what they do and how they work because they're useful.
And finally, some examples of circuit components are ammeters, voltmeters, a cell which can be made into a battery, a bulb, a resistor and a variable resistor.